Let's talk about ionic bonding now. Ionic bonding, actually, a lot of times we discuss in contrast to covalent bonding. So it's definitely worthwhile to sort of recognize where some similarities and differences are. That'll be kind of introduced here in this beginning with the review bit. So let's kind of do a couple of things. First of all, ionic bonding. Right? When it comes to reviewing, let's go ahead and take a look at this first sentence. Any substance with a definite composition involving 2+ elements, well, that is a chemical compound, just like we've seen before. That's not really changed, right? We're talking about definite fixed ratios or fixed proportions anyway of definite, right? Of definite, that's what that means, involving 2 or more elements. Next one, a chemical compound where its elements are ionically bonded. Well, hey, what do you know? These are going to be called ionic compounds. Now, with ionic compounds, a couple of sort of characteristics. First of all, the elements in this bond are typically involving metals and nonmetals. Right? And you see some examples here. That says nonmetals. The table salt is an ionic compound because it's made of a metal, sodium, and a nonmetal, chlorine. So sodium chloride, that's an ionic compound. As a non-example, then, our friend sucrose, which is basically table sugar, is not an ionic compound because it's made of only nonmetals, C's, H's, and O's. None of those count as metals. All right, let's take a look at this first term here. This is a bit of review, kind of briefly mentioned. Let's go ahead and break this down a little bit closer, a little bit more carefully, though. This says the simplest repeating unit of an ionic compound is something called a formula unit. All right, now this again is something we briefly mentioned before. But basically, this can be used as sort of the analogy to molecules for covalent compounds. Let's go and kind of figure out what's up, though. So these ionic compounds exist as a network, right? A network of positive cations and negative anions, where I can't really find an individual molecule. So let's kind of break this, or zoom this in a little bit. So our friend sodium chloride here, right? This has been shown a couple of times, where you have, again, a couple of different purple and green atoms. And these purple and green atoms, right, they're not really a single isolated unit. They're all part of this giant network. And you see here kind of the structure where it's a bunch of repeating purples and greens. And that's a nice indication that this is going to have to be broken down to where if you want to ever analyze anything, right, it would just be like this. These two that are circled right here, that counts as a single formula unit. A single formula unit then is repeated over and over again to make this giant network. Alternatively, right, if you're given this giant network of things, you kind of have to sort of work backwards and maybe figure out what is that smallest repeating unit. And it turns out it ends up being our friend NaCl, 1 purple and 1 green. So that's the main difference between the ionic structure and the molecular structure, right? Covalent structures. So in this case, right, we're talking about a giant network of different, of repeating formula units, whereas this right here is just a single molecule. Let's go ahead and review some terminology here. The formula unit, therefore, is the representative particle of an ionic compound. Like we said earlier, it's kind of like the corresponding molecule, which is the representative particle for covalent compounds. So you can see right here, I've kind of talked through this already. The formula unit for table salt, sodium chloride, involves 1 ion of sodium and 1 ion of chlorine, which again represented by 1 purple and 1 green. And so this single formula unit is repeated over and over again to make the network. Or, for example, barium fluoride happens to contain 1 ion of barium and 2 ions of fluorine to, again, make 1 formula unit, right? That's exactly the single repeating unit that makes the ionic compound exist. As a non-example, right, sucrose combines 12 atoms of carbon, 22 atoms of hydrogen, 11 atoms of oxygen to then form 1 molecule, right, which again is different because it is its own isolated group. And finally, non-example, water combines 2 atoms of hydrogen, 1 atom of oxygen to once again form a single molecule. So what kind of helps here is recognizing again the composition. These non-examples like sucrose, these have carbon, hydrogen, oxygen, those are all nonmetals. Whereas our friend barium and fluorine, that's a combination of a metal and a nonmetal. So that together knows that you're going to look for the term formula unit. Finally, this one right here is not particularly new. Blank, the written representation of a compound using element symbols and subscripts representing the number of atoms of each element. This again is just a chemical formula. That word formula, right, is basically applied to any kind of compound. Doesn't matter if it's ionic or covalent. So you can see right here. Here is a chemical formula for sucrose. Here is the chemical formula for sodium chloride. Let's talk about formation of an ionic bond. There's a lot of parts that go into this, but it really is, again, just sort of the same idea here. It all comes down to this potential energy. When a non-metal atom and a metal atom approach each other, each atom is attracted to the valence electrons that's supposed to be involved in this bond, right? Kind of like we saw with covalent stuff, right? When you kind of bring them closer to each other, there's going to be some attractions between a nucleus of one atom and the electrons of the other. The nonmetal atom has a greater attraction to the valence electrons, whereas the metal has a weaker attraction to the same valence electrons, right? So again, as two atoms approach each other, those outermost ones which are about to form the bond, nonmetals have a much greater electronegativity. So why, right? Electronegativity of the nonmetal is much, much greater than that of the metal, so that the nonmetal will be more attracted to those electrons that are about to bond. In fact, it turns out the difference in attraction is so great, the nonmetal atom receives a valence electron from the metal atom. Right, so almost basically, not necessarily ripping it off, but it pretty much takes it away. And so this process is known as electron transfer, right? Or exchange. And the word exchange is kind of misleading. Right? Exchange suggests, there's something that goes from one atom to the next, and the other atom gives something else up to the other one, right? Kind of like a trade of sorts. Not really exactly how that works. It's more of like a giving. It's more of a transfer, to where one substance gives up an electron, the other one just receives it. And so in a bit of a way, it's kind of like a one-way gifting, as if one of the atoms kind of forgot to get a gift for the other one. The point is, each atom takes or receives enough electrons to complete their octet, of course, which you probably recognize now, where each atom will have then 8 electrons as a result of it. So this kind of chart right here, anyway, breaks down a lot of what goes on. So let's say we start off just with our friend sodium and chlorine. These are plain atoms. These are neutral. These have not bonded. They're their own individual atoms. You can see right here, the types, right? Sodium's a metal, chlorine's a nonmetal. No surprise. Let's take a look at their electronegativities. Well, 0.93 is fairly low versus the 3.16 here, so where the difference is 2.23. And that difference, again, is well beyond that 1.7 cutoff that we learned before. And so we know that this is going to end up forming an ionic bond, right? So what exactly is involved with the ionic bond is now, right, because electronegativity for chlorine is so much higher, it's going to tug on that electron that sodium is contributing much, much greater than sodium will. And so as a result, chlorine takes that electron, whereas the sodium will give up that electron, right? So we're not, kind of magically gaining an electron or losing an electron from thin air. They're taking it from one another. And as a result, right, because you gain an electron, this is definitely wrong, you have a -1 charge with our friend chlorine, and then a +1 charge with our friend sodium, because sodium lost the electron, chlorine gained the electron, and so as a result, right, the negatives kind of happen to where you gain or lose that +1 or -1. Finally, the resulting ion, right, represented as Na with a positive charge there, chlorine with a negative charge up there. And so these resulting ions then basically attract each other. So that's what allows you to form one formula unit. So this combines to make one formula unit. Now, this is important to recognize that this is a little bit different, right? We're not actually talking about just two things kind of joining hands and coming together. This is kind of where it's like a two-step process. Atoms come together, one takes the electron, it forms an ion, the other one forms an ion, and then they kind of attract each other. So there's a little bit of like a two-step process here, kind of like you see here. For sodium, 1 electron, chlorine, 7 valence electrons. To make it stable, right, our chlorine will completely take away that electron, right? So that transfer from sodium, giving it up, and therefore, as a result, sodium is positive. It doesn't have any electrons shown here, but it's also got its octet satisfied because there's an energy level sort of underneath it, sort of embedded in there, not shown. And then chloride, as a result, has a bunch of electrons, now 8, and now has a -1 charge. All right, now let's kind of break down this next idea here. This next term is called lattice energy. So ionic bonding is a result of atoms minimizing the, you guessed it, potential energy. Right? We want to minimize the potential energy. That's why any bonds form, resulting in ions that are more stable compared to its individual atoms. Right? So individual atoms are generally considered less stable than a bonded form of the atom. So potential energy actually is minimized by arranging atoms in a lattice. All right. Sometimes you also might see this being called a crystal lattice. So either of these terms is appropriate. I'll probably use crystal lattice more frequently. But this is that repeating orderly arrangement of the cation and anions. Now you probably recognize, again, that the word crystal shows up here. You kind of imagine what crystals look like. This picture on the right sort of shows that. It's like this sort of very repeated, very geometric shape. And that's kind of the case, right? We actually see that not only on the outer scale, right, the big scale, we kind of see on the small scale too. Anyway, the point is, this maximizes, as you get it, attractions and minimizes repulsions, right? So there's always going to be some amount of those because there's always positive electrons, or sorry, positive protons and negative electrons. So in this example to the right, you see our friend's calcium fluoride, CaF2. It's actually going to adopt kind of a crystal lattice. So if you look at this like tiny scale, if you zoom in really closely what that looks like, it's kind of arranged in a way to where, you know, these purple atoms are kind of far from each other, and because these green ones are sort of arranged to keep them away from each other in the same way that the purple sort of keeps the greens away from each other in a very specific pattern. Now, exactly how that distance works out, we're not interested in. That's a little bit beyond our scope here, but it does have a repeated pattern. And the repeated pattern then is manifested by this guy, right? See how this thing kind of also has a very geometric repeated shape? That's that crystal lattice. So we can expect that on the level of atoms and ions, that structure will definitely show in the visible part, where we know that because it's so orderly and arranged here, it'll look orderly and arranged with our naked eye. So let's move on to the next point here. The attraction between the ions in the crystal lattice is represented by something called its lattice energy. This is the energy that's released when ions come together to form 1 mole of an ionic compound. Turns out the values are negative. I'm going to pause there for a second. Why are values negative here? Well, again, let's kind of take a look at the language from before. It says the energy that's released, right? Energy is going away. We lost energy. And that's why we use a negative value. Furthermore, it's reported in units of kilojoules per mole. That should sound kind of familiar. Because if you kind of are trying to bridge connections again between the covalent molecules and the lattice energy here, this is kind of like the same thing. These are more or less the representation of strength of attraction. So let's kind of try this out. First of all, large lattice energy. This means that a large amount of energy was released. Right? High lattice energy means that a lot of energy was released, which means that the resulting ions have become more stable. And therefore, we know that these ions, because they're more stable, are therefore more strongly attracted to each other. So once again, large lattice energy, meaning you give off a lot of energy, right? Large amounts of released energy. That means it's very stable, which means that these attractions are very strong. So you can also take it the other way, right? Kind of saying, okay, what if I have a low lattice energy? Meaning only some, like small amounts of lattice energy, right? Or they say small lattice energy means that small amounts of released energy is present or has happened. And then that means it's not as stable, right? Not saying it's not stable, just saying not as stable. And now your ions are kind of not as strongly attracted to each other. A lot of this again comes down to just sort of relative comparison. So it's not exactly 1 for 1, but you know, it gets close. It gets close enough. So using table 3 to the right here, if I'm going to take a look at these exercises, I'm going to kind of break down what's given to me. So based on this, right, this is the lattice energy of some common ionic compound. I have 2 columns. One lists the compound, the other one lists the lattice energy. So this energy again is presented to you as a negative value here, 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 so on and so forth. And of course, this gives you an even point of comparison, which is kilojoules per mole. So the question asks, identify the 2 compounds that have the greatest lattice energy. So what would that look like? Well, if you're looking over here, right, you kind of talked about there being a large value. And so if you notice the biggest ones, I'm going to highlight them just with an arrow. Looks like it might be this one and this one. All right, so for those of you who are kind of wondering, okay, how exactly do the negatives figure in? Well, the negatives, again, show you that it's a very large negative value, right? So negative 3760 means that this released 3760 kilojoules of energy. Whereas this one right here, right, this one releases 2600 kilojoules of energy. That's a large amount of energy. That means it's going to be a large lattice energy. So I don't really want to compare this as sort of like an actual value, right? Because negative 2634 is actually a bigger number, at least a higher value than the negative 3760. But again, we're considering this as a negative comparison. So negative 3760 is a larger lattice energy than calcium, which is a negative 2634. So those 2 are the ones I want to focus on. So that'd be CaF2 and then MgO, with MgO being the larger one. Identify the 2 compounds that release the most energy when its ions come together to form 1 mole of compound. Well, that language of its ions come together to form 1 mole of compound, that's the definition of lattice energy. So basically we're saying which one releases the most energy. So basically which one has the greatest lattice energy. Once again, it's still these 2 compounds, CaF2 and MgO. Identify the 2 compounds with the most stable crystal lattice. Well, because these released so much energy, these are also going to be the most stable amongst this list. So again, I can go ahead and point out these 2. And finally, identify the two compounds where its ions are the most attracted to each other. Well, I think it kind of makes sense that this kind of all goes in line with each other because they're the most stable. These two are going to be the most attracted. I'm going to cut that off there. Then let's go and try it out. Identify the two compounds where its ions have the weakest attractions on this list. Right? So again, it's important to recognize that the attractions are still there. They're still attracted to each other, but these just happen to be the weakest ones on this list. So I'll use blue to kind of recognize this guy, right? And this dude, so 751.4, negative 715. Those again are the weaker ones. In case you're wondering, KCl is definitely the weakest of all of these on this list, and the NABR would be the second weakest. But either way, it's kind of how you kind of break down those values. Finally, let's kind of break down again. Here's a couple more ionic properties. So when it comes to ionic properties, we'll talk a little bit about just our ionic properties as a whole, but they're a lot easier to compare because they tend to be more consistent versus covalent compounds, which have a very wide variety of properties. So ionic compounds are easier to describe in broader strokes. First of all, they definitely have higher boiling points, and they definitely have higher melting points, right? Which means it takes a lot of energy for them to melt, which means going from a solid to a liquid. And then it also takes a very high temperature to go from a boiling point, or to get to a boiling point where it changes from a liquid to a gas. We're talking about scales of like 800 degrees Celsius up to like 2000 degrees Celsius, right? Remember, for reference, boiling for water is at 100 degrees Celsius. So for ionic compounds, that's 800. That's a lot more temperature, right? A lot higher temperature anyway. Also, at room temperature, most of them are also solid states. We can generally expect ionic compounds to be solid state. Why is that? Because at room temperature, that's kind of cold when it comes to solids for ionic compounds. So basically, we have high freezing points too. Right? It does not freeze at low temperatures like we're used to. Generally, it also has high hardness, right? These don't really deform very easily, unlike some other things that might be a little bit more malleable. Conductivity, right? So this is the definition about how to carry current. High conductivity, low conductivity, no conductivity. When it's a solid, right, no conductivity is possible when the ions are frozen as in a solid state, right? That means all of these ions are all kind of locked into place, so they're not going to necessarily move around freely. It can't carry current. But conductivity is possible when ions are free to move when it's dissolved, right? Usually in water, or when it is molten, right? Molten, or again in its liquid state. So when things are free to move about. Now you kind of recognize that as particle motions, so that kind of makes sense too. So current's only possible again when it's dissolved or when it's molten, when they can freely move about. And finally here, this last bit, this is something that is used to describe this ability of it to break apart from an applied force. We call this basically brittleness, right? So these are actually fairly brittle. These ionic compounds, even though we talked about them being hard, they're also brittle because it can kind of be applied, or some force can be applied to where it sort of breaks apart. In fact, it demonstrates this property called cleavage, where when you kind of basically cleave a ionic compound, because when you put the force, it separates into more crystals that are also smooth and flat. So you can kind of see that right here on the right side. This structure right here, you definitely see some kind of nice cubic shapes, and it's also pretty smooth along those parts where it broke off from the rest of the structure. And how that kind of looks on a more microscopic scale, right? Looking at an ionic crystal, you apply this force, kind of misalign these for just a moment. That little split couple of picometers will allow these positive and positive line up against each other, negative and negative line up each other. And what do we know about like charges? That they repel. And so it'll break apart in nice, clean, even, smooth lines. All right, that'll do it.